Hello? Can everyone hear me? Yep. All right, put your laptops away. Yeah. Okay, so let's get started. So homework 1 has been posted, and there's some stuff about test 1 that's been posted. So today I'll be talking about those things. Although the way I'm going to teach is I'm going to start explaining homework 1 and then talking more about linked lists. The way I want you to work on what you should be doing for this week and the next is try to work on the test questions first before you work on the homework. Okay? Because the test questions give you the basic background that you need for the homework, and I'll talk more about this during the lecture as well. This is annoying. Okay, so what is it that that the first homework says? It says that you will get this file called Shakespeare_cleaned.txt. So you get this file which has all of Shakespeare's text tokenized word by word. And there's a particular question you have to answer. Like your program will get queries, and the queries are for any word length L and number K. What is the kth most frequent word of length L? Okay. So the way that you would attempt such a question is you should never think bottom up. So bottom up is like, oh, how am I going to read the words? Or where am I going to print the words? Don't worry about the I/O aspects at the beginning. First, before you start coding, you should work on paper and try to think. The first question is, what is the data here? The data is the words of Shakespeare, right? And the way you think as a computer scientist now is, how do I store this data? Once you kind of make a mental model and you draw it out on paper, and you figure out a way of how to store the data, then you can start thinking about, how do I answer the questions? How do I actually write the code? I know many students will immediately try to start coding, do that for like hours and hours and get stuck, right? And you should not do that. So first you have to think systematically. And just to explain, why you have to think systematically about this. So here is, let's see if can you see this? Okay, so this, just to show you this is what the original text that I got looked like, right? So it has all of this, and the way I parsed it, the file that you will get is, actually I think you're going to get this file, is you get this file on the left over here. So what I've done is I've basically taken this file, I've parsed it word by word, and I've removed all words of length less than like 4, and so you can see all the words are listed down over here. So this file to the left is your input file. Does that make sense? That's the file that you get. Okay, so that's a file that you need to read. And if you think about, so let's see, sorry here, I'm just going to, the number of words that you're getting in this text, it's 319,000 words, down here if you see. WC does word count. So there are 319,000 words in this file, which means that debugging this program can be pretty hard, because you can't just like look through the file and say, oh, did I get things right? Right? So you have to be really careful when you do this. So the first question is, how should you store the words? So what is the first thing that comes to your mind? How should you store the words? Yeah? Don't look at the assignment, but just, yeah. You would guess an array. So string, each word is a string. But you have 319,000 words. So you're getting ahead. Linked list, yes. But the first thing is you would store it as an array. That's the first thing that at least I would think about. And indeed, this assignment you could do with an array. Okay? But in general, why should you not use an array? Yeah? Memory intensive. Yeah? You can't dynamically allocate it. Exactly. And right? So most of you, or at least those of you who've answered, seem to be answering correctly. The reason is, when you define an array, you need to decide how big the array is beforehand, right? And in this case, of course, you can always figure out how many words there are by making a pass through the file. But in general, suppose, now this is a simple example, but Twitter actually stores all tweets, right? All tweets probably, ever. Can you imagine how much that is, right? And every day they're not going to know they don't know who's going to do something crazy today, and then Twitter explodes, right? So because of that, it's hard to decide what the size of an array should be beforehand. Now, you might say maybe you could use a vector. But a vector is also really just an array that's just resizing under the hood. So this is an example of a place where you would use a linked list. And so now I'm going to start writing as opposed to this. And so let's get the document camera up and running. Okay, hopefully everyone can see this. So before we talk about linked lists, again, I think this might be, you might know about all of this, but I'll just say problems with using. By the way, everything that I write here, all this will be scanned and will be on the website. So you don't have to copy it necessarily. I will, as I said, all of the lectures are being recorded and webcast. They're available through Canvas. I did not put up the first lecture on YouTube because it has things that are really specific to the course that I don't want to make public. But everything else that I say that I think can be made public, I will make public. All right. So the problems with an array is we do not know a priori, which is basically, I guess, Latin for beforehand. We don't know a priori how long the array should be, right? So we don't really know how long the array should be. And so normally when you allocate an array, you have to specify the size, right? Okay. Now you might say, well, okay, so what I'll do is I'll allocate an array, and if I actually outgrow the size, then I can increase the size. I can do things like that, right? That's usually what a vector does. That's called that's a dynamic sort of like a dynamic array. But there's another issue is that if you think about memory, an array is a contiguous portion of memory. That's what an array looks like, right? So maybe this is being used up, and this is being used up, this is being used up. Okay, how many are familiar with how memory is arranged? Okay, sort of, kind of, but so essentially think of memory as just being like this really, really long, it's like a tape, right? And things are being stored at various places. So an array is like this chunk that is, it's called contiguous because it's in space. Think of like continuous in space, right? And so the problem is, suppose there's free memory here and there's free memory here. An array cannot use both of these. It has to use only one of them, right? So if you want to make your array bigger, sometimes you can bump into some things and it becomes complicated. And so how many of you are familiar with linked lists? Okay, most of you. So linked lists don't have that problem. Yeah?
Why not use a hash map in this instance rather?
So you're getting even ahead. So the thing is, how do you implement a hash map? With buckets. How do you implement those buckets? There you go. That's why you need to know what a linked list is, right? Because a linked list is the most fundamental data structure on which all of these other things are based. Yes, in the back. So usually your OS will then throw an error. That's when your program will crash. Sometimes you'll get a core dump, out of memory, some kind of problem of that form. it depends on how benign your OS will handle that issue. Right? So again, to get deeper and deeper into this would be to get more into systems, which is not the point of this course. Just want to give you a hint as to, yes, okay, so you need to think a little bit about your data structures, and the benefit of a linked list is that you don't need contiguous memory, and you don't need to know a priori how long the array is going to, or how many words you need to store. So again, the Shakespeare assignment is an example of something where if you got such a long file, unless you were to process the file, you wouldn't really know how long to make things. Okay, so now let's go back to what we're trying to do, right? We're trying to store all these words here. So again, before we start, or you start coding, it's worth writing down what is it that you want from, it's like write a specification of the structure, the data structure that's going to store the words. So the first thing you would imagine is you are going to go through all the words and you're going to record the frequency of every word. Right? And then you're going to have to process this some other way. The first step is going to be get all the words, store their frequencies. Which is why maybe someone suggested a hash map, because saying a hash map is the obvious way of doing it. But I'm not allowing you to use libraries or built-in data structures. So given a word, W, so I'm thinking of this file that you're reading, and all these words here, there are these words. Let's just say your program is reading these words line by line, right? Word by word. What do you need to do with the word? So you get a word, what is the first thing you need to do? Yeah? Compare it to the rest of the words to the list. Right, but is there another more direct way of saying what you're saying? What is it that you're trying to do, yeah? So no, just tell me more like, so you're getting into details. Like you'll see my answer what I'm looking for, yeah. Okay, you want to add it to a, so you want to, okay, good. So you want to insert the word into a list. But before you insert, is there something else you want to check? Yeah?
Put more in English words.
Have you seen this word before? Exactly. Have I seen this word before? It seems like the first thing you want to do is to check, has this word appeared before? And that is often called find. Right? Is W already present in the stored words? Then you do, suppose it's not present, then you would do insert, which is if W is not present, like add to, well, I'd say like add to your list of seen words. Okay, fine. What next? Yeah? Add the number of occurrences, right. So if the word is already present, you would update your frequency, like increment. Right? So I'm going to refer to this as an update, which I'll just say is like, update frequency of W. Now, for this assignment, you don't need this, but you could also imagine there being a delete, although you don't need it for this assignment, but it's natural to have a delete, which would be remove W from the list of seen words. You only need the first 3 for the homework, but in general, you would need these 4. Now, what is interesting is that this is a specification on the structure that is storing the words. It's not an implementation. It's basically saying this is what you want, whatever structure you're storing the words to do, And this specification, okay, it has a technical term. The reason I write it this way is these operations, and actually it's just the find, insert, and delete, not even the update. But these operations, these define what's called the list abstract data type. This is also called an ADT, meaning what this basically says is the list ADT says the list, this is a specification that given a collection of items will find, insert, update if you want, and delete, right? So your aim is to have a list structure that stores these. And then you need to build an implementation of this list. Am I making sense here? There's a distinction between the specification and the implementation, right? And the reason that you need to have this way of thinking about things is so that when you have a complicated project, I mean, homework 1 is not very complicated, but you could imagine it's probably more complicated than many things you've written. Unless you break it down into what is the specification, what's the implementation, your life will be hell when you debug. Okay? So now that there's some sort of clarity, in, okay, so this is what I need to implement. And this list ADT is like, this is an abstract representation of what needs to be done with the structure that's storing the words. Now you can implement this using an array. You can implement it using a hash map. You can implement it using a linked list, right? So when you're talking about those things, those are the implementations of what you need. And so in this assignment, you're going to implement as a linked list. So in a linked list, you can do all of these operations. In an array also, you can do these operations. Okay, now does that make sense? Okay, good. All right, so now let's proceed. And so just to sort of list out a few things here, what are the benefits of this implementation? So the benefits is that it allocates sort of exactly the right amount. Can everyone read what I'm writing? Like, is it legible? Does it make sense? Okay, good. All right. How many people still write cursive? See? That's why I'm checking, right? That's why I'm checking. How many people still write? Maybe you don't even write anymore. You just type, right? Yeah. Okay. How many of you have actually seen a fountain pen? Do you know what this thing is? Right? This thing, it's a pen. You actually fill ink in it. You know, like you open this, and there's a cartridge in here where I fill ink. And maybe you can't see this. There's ink in there, and then when it finishes, I actually put more ink into it. Yeah. Do you know how much this thing costs?
Where's the battery?
It's not bad. Yeah, it's something around that. How do you charge yourself? Yeah, I know. There's a little thing that I plug it into. Okay. Yeah, exactly. It's a little ridiculous, right? It almost costs like as much as a phone. Well, not an Apple phone, but you know. And all it does is write. But then the thing lasts 50 years, whereas your phone lasts for 1 year. So that's the difference. Okay, so it allocates exactly the right amount of memory. If you pay attention, you'll see more pens during the course. Like I will, once this finishes, I'll bring another one, then another one. Okay, it allocates the right amount of memory. It doesn't need an initial size. And thirdly, it is not contiguous in memory. Now, of course, there are benefits of being contiguous in memory. There are benefits that an array implementation can have. So in reality, if you're doing this, maybe you want to use an array for various things, right? There are pros and cons of everything, but it's important to know what are the benefits of this implementation, the linked list, over another implementation. Okay, so far so good. So now let's actually get into the implementation of a linked list. I'll try to write some, sort of C++ code. We'll talk through it. I'm hoping that many of you are how many of you have actually written a linked list by yourself? Okay, most of you in C or C++. How many have done that? C, C++. Okay, so then hopefully, do you still want me to go over it? Yeah? Okay, all right. So I can, all right. Okay. No, it's good to see things that you've seen before. It gives you a warm and fuzzy feeling that I understand what's happening in class, which is important. It's important. Okay, so how does it work? So we're going to start with a class node. So this is your node object. Okay, now for the assignment, your node object, your node always stores data and a pointer, right? The data that you're going to store for the assignment is going to be probably a word and a frequency, right? Now, for the sake of my writing, I'm just going to assume a linked list of integers, right? So at this point, I'm sort of stepping a little bit away from the assignment and just saying, let's talk about an implementation of a linked list of integers. So we have some int that I will refer to as data. And in general, this could be any object, really. You could have a linked list of images. You could have a linked list of linked lists. You could have a linked list of whatever data type you want. And again, what you choose the data to be depends on what you're trying to do with the implementation, right? Okay. And then this is why we teach recursion. We have a node star next, which is a pointer to the next node, right? And that's what it is. So sort of just to draw a picture, this is the common picture that you may have seen. You have your data here, and then you have next over there. So this often is drawn as like, I have a number, 42, and then I have a pointer to something. Right? This is sort of how we draw this. And often if I want to show null, that's that. So this is what I'll just call null, which is just a pointer, which is like an empty or a zero pointer. So this is your class node. This is like the first thing that you would write. And then let me just write a constructor. So again, if the C++ syntax is bothering you, so I think there are lots of questions of, do I have to do it in C or can I do it in C++? I don't care. C is a subset of C++, right? I'm just going to compile your code, get an executable, and make sure it works. So if you want to do everything in C, that's fine by me. I would use this as an opportunity to learn some C++ syntax. It's not that much more difficult. And especially with the classes, you'll find that it's more convenient. But again, you can write just C code. For the tests, it'll just be C code, really. Okay, so how does this work? So this is just saying that the constructor says if I get this, and I'll just put it in the same line, next is equal to null. Right? This is saying that the constructor will take some integer, and it will output a node which has that integer, and then the second pointer is null, right? Because it's just like it's a node by itself. Okay, questions? Is this clear? Okay, yeah.
Yeah, it's been a while.
Yes.
The constructor doesn't need to be inside class definition.
So if I put it this way, then I can put it outside. If I put that double, otherwise I would stick it into there. The reason I don't do that is then, like with paper, it just gets messy. Yeah. And I actually forget what I have in my implementation, but you can see. I don't know which one I've done. I've done something. Okay, so this is a node. So once you've defined what a node is, you can define a linked list of nodes. Right? So the linked list is built on top of the node class. So this is the class linked list. Again, all of what I've written here, all this code is available in that Codio box called linked list. Right? All the code that I've written here and more is there. So there's really just one sort of field that it has, which is a pointer to the head. And this is the pointer to the first node of the list. Right? And then the constructor, which I'll put down here, the constructor, when you initially construct the linked list, it just sets the head to be null, and that's it. Right? So this is like the bare bones structure, right? This is how you're building it. So initially you have a node class. The node class is a constructor that takes a value, which would be an int in this case, and constructs a node with that int. And then you have a linked list class, which now basically when you construct the linked list class, it just creates a pointer called head, which is assigned to null, which is that the list is empty. Right? And now you need to start building the list by inserting things into it. Yeah, sort of seem familiar, sort of kind of, everything looks good? Yeah. I'm making a singly linked list. So essentially, the more pointers you put in, the more ways you have of shooting yourself in the foot. So minimize the number of ways to do that, right? So if you don't need to make a doubly linked list, don't make a doubly linked list. But yes, you can. You can have a head pointer and a tail pointer, and you can have things that are going back and forth. I mean, things are awful enough with just one that with two, it's just worse. But yes, you can. Yes?
Make your code dumber.
Exactly. Make your code dumber. See? There's a smart person speaking. Yeah. Like Brian Kernighan's quote, like something about it has resonated. Yes. So again, yes, you can do a doubly linked list. You can make, yeah. So again, in your homework, as I don't care which linked list you make, but the implementation that I've provided is a singly linked list. Yeah. Okay. So now let's just talk about how we would insert into a linked list. So now I'm going to be a little sloppy with the syntax. I'm not going to put the class double colon and what. I'm just going to write the method as is. So let's say you want to insert. How many of you still have the post-its that I gave? Most of you have them. So in case you need them, they're down here. The reason I give the post-its is this is like my low-tech version of clickers, where I ask a question in class and then I'll ask you to show a post-it for the answer, right? The reason I do low-tech is that way I don't need to use my laptop either. If any of you need post-its, they're over here. So why post-its? So okay, I'll give a couple minutes for you to pick up one of each color. One of each color, please. Okay, that took a while. So why don't you all sit down and I'll just pass these around, because this is going to take a while then. Take one of each and pass it down, and if you already have them, just pass it down. Take one of each, pass it down. If you already have them, just pass it down. And same, take one of each and pass it down, and you get it. Okay, so why am I doing this? Because now, since most of you have seen linked lists, I'm going to ask you what the answer is over here. So the code to insert in a linked list is 4 lines of code. The first is you got a value, so you want to insert 42. So why 42? What? Why? Huh? Exactly. It's the answer to everything. Precisely. Huh?
What's the question?
It's this course. This course is the question. All right. So the first thing we'll do is we're going to create a new node with this value. And so I'm going to call this node the latest, because it is the latest node. So it's a new node with this value. Okay, so I created a node. The next line is I have to link the node to the existing list, which I'm not going to tell you what it is, but I'm going to give you some options here. So there's going to be some line of code that links this node to the existing list. Then I reset the head, and then I return. Okay, so the question is, what line goes there? What are the colors that I've given? Red, green, and blue, right? Okay, so all primary colors. So I'm going to give you 3 options, and you have to tell me which of these is the right answer. You don't have to show the answer immediately. Usually when I ask a question, I allow you to talk amongst yourselves. I'll give you a minute or 2, and then I'll say, what is the answer? And you can show me the answer just putting up the, I was going to say the node of the right color, but I mean the post-it of the right color. Okay, so what is this going to be? Is it head arrow next is equal to the latest? So that is option red, option blue is latest is equal to head, or option green is latest arrow next is equal to head. So I'll give you a couple of minutes. You can talk amongst yourselves if you want, if you need to. And then when I ask you to show the answers, please raise your hands. You don't have to raise your hands right now. And that way you can look around and see what other people are also saying. I'll give you a minute. So what is the option? Okay, all right. So there are 2 reasons why I ask questions in this way. The first is answer honestly. If you don't know the answer, then I don't know, just don't raise your hand. That way I get some sense. I get some visual sense of whether people understand or not. The second reason why I do this is so that you don't go to sleep. It's very hard to go to sleep if people around you are talking. And so, okay, so what's the answer? Raise your hand. Okay, so most of you have shown green, and so some of you are maybe a little confused about it, but I think most of you got it. So the right answer is latest arrow next is equal to head. So let's just go over a small example to see why that's the case. So here's my current linked list, and I'll have 10, 101, 5. Okay, so now I want to insert 42, right? That's what I wanted to do over there. And so I've created this new node 42. So when I first ran, I'm sorry, so let me zoom out a bit. So first ran the constructor, I got this new node which was linked, just that, like so. Now what you want is, okay, so in general, the easiest way to insert in a linked list is to insert at the head, not at the tail. So you insert at the beginning of the list, and that way your code is the easiest. So you want to insert this at the beginning of the list. So there are really 2 things that need to be done. First, you have to link this to the existing list, and then you have to reset the head pointer. So the reset the head pointer is being done there. That's the next step. So the way you link is you say, well, head was pointing there. So you want and this is latest. Right? And the way to think about these things are themselves pointers, right? These are like some pointers, addresses to these nodes. So latest arrow next is that pointer there, which is currently what? Null. Currently latest arrow head is null. So you set latest arrow next to be head. And if you did that, on running this line colored green, this will point to that. then you have to reset the head pointer. The head pointer now needs to be equal to latest. So then that becomes that. So a major point of confusion that people have is when you reset, when you change latest arrow next equals head, you're not changing latest. The address of 42 does not change. You're changing the address of what 42 points to, right? So when you run this line here, you're not changing what latest is. Latest is still pointing to 42. And then you reset the head. Any questions? Is this clear to everyone? Yeah? Yeah.
In C, wouldn't we have that passed in the head as a pointer rather than having it through the
So the thing is, in C, yes, you would have to. So I'm assuming this is C++ code where this method is inside the linked list class. Yeah, good question. So that's one of the reasons why you should use C++ as opposed to C. Otherwise, you have to keep passing all these things back and forth. So so I should have said this. The right way to think about this is inside the linked list class. Right? So the linked list class is on this. So I'm just writing each function method separately. Okay, is that clear? Okay, good. So insert is quite simple. There are no gotchas in insert. So going back to what we said initially, that is pretty straightforward. The next thing we need to do is find. And find is often also referred to as a traversal or sort of walking through the list. And so, so we'll do find. Now I'm going to implement find to actually have a return type. So what this is going to do is it's actually going to return a pointer to a node, so just a node, some node with val, and it will return null if no node exists. You can also implement it as a Boolean type, which basically would just say yes or like true or false. It's more convenient to do this. That way you actually have access to a node that has the value. Okay? All right. So just to make things more challenging and to give you more practice with recursion, let's implement find using recursion. Okay? So no loops. Right? And we'll do that for delete as well. So for what it's worth, in the codes that I've shared, there's probably a separate folder called functional where all of the implementation is done through recursion, everything. Okay, so firstly, why use recursion? You'll see that for coding up more complicated functions of linked lists, recursion is actually easier to deal with. And secondly, practice in recursion is important for everyone. So how is find val going to work recursively? Let me just write out the logic. So I'll write out the logic without giving a base case. So the base case should hopefully be obvious. So the first thing you do is you check if head arrow data is val. Right? I mean, that sort of makes sense that here's your linked list. So this is head. So first check if head has the data. If head doesn't have the data, recursively check starting from here. Okay, so if not, recursively find starting from head arrow next. And I should have written this before, but again, the 0th condition is that if list is empty, return null, and check if this, then you would return the head. Now this is actually poorly written pseudocode, and you'll see why. But it explains the logic, hopefully. So what you do is and this is how lots of recursive implementations of linked list functions are done. You do something with the head, and then you do a process recursively with head arrow next. Okay? Yeah. Good. Yeah. So it's not going to be head then in the recursive implementation. Exactly. Right? Good. I don't know if everybody understood the question, understood the point. So the point is, again, this was poorly written pseudocode, because if you think of a recursive implementation, the recursive implementation cannot keep using head, because head is only pointing to the beginning of the list. Right? So somehow your recursive functions have to be looking at other pointers, which is why in recursive implementations, you'll see some overloading. You'll see there are two functions. One is what I call a dummy function, where it simply calls another function with a different argument, and then that's the recursive function. So let me do this. Let me write this out carefully, and you'll see what I mean. So here is my recursive implementation. Again, I'm overloading the function. I mean, I'm going to write two functions with the same name but different types of arguments. So the first one is just going to be, right? I'm going to return find with two arguments, val and head. So let me write this, and then you can ask me questions. Then the real function is over here, where I have an int val. I have a node that I call start. So start is going to be some pointer in the list at any intermediate stage. Now the way that start, okay, so let me see if I think I can shove everything into this. So if start is null, return null. This is the base case. If start arrow data is equal to the value, return start. Right? So this is found. And now for the last line. So I have to now return something. Again, now I'm going to give you three options, and you tell me what it is. So I have to return something here. You know what the problem with coming up with these questions are? It's very hard to come up with good, wrong answers. Right? For me, it takes a while to come up. I have to talk to many of you, and then I start saying, oh, this is the good, wrong answer to check if you understand or not. Okay. So, all right. So here are my answers here. So so far, does this make sense? Right? So what I've hidden is actually the real part, which is what is the recursive call. So I'm giving you three options for what goes over there. Do I return find val of start? Do I return find val of start arrow next? Or do I return find val of head arrow next? Okay, so I'll give you a few minutes to think about it, give you a couple minutes, and then you tell me what this is. Okay, all right. So what is the answer? Right, good. So whoever has raised their hand has the answer. There are somewhat fewer of you who have raised it, but that's right. So this is the right answer. So you find the value. So you can't do find val start because find val start is actually that's the initial call. You don't want to go back to the head because this is at some intermediate point in the list. So what you're doing is you're finding the value at start arrow next. So the way, okay, so maybe I should like questions. Yes. Why can't you use? I'm sorry.
Yeah, like why do you have two? Like why can't we just use the second find? Like why do you need both?
You have to initially call it from the head.
Right, but then you just pass the head to the second. Like couldn't you just call the second find? Like just have one.
You could have just one find where you would also give the head, but it's nicer to have one function that you expose to the outside world, which doesn't give the internal. So often, sometimes they'll make this public and this private or something like that. That's again so that the syntax for this function looks like syntax for the non-recursive version. Yes. Yeah. So I'm not dealing with I'm not dealing with public, private, and things like that. But in general, that's the way that you would do it, right? So yes. It's a good question. So why should you do it recursively? So okay, one is conceptually, it's a lot clearer. Secondly, recursive code will often it will throw compile time errors, not runtime errors. Whereas it's easier to throw runtime errors when you do it iteratively. Now the cons are recursive code is often less efficient because of this underlying stack has to grow and then the call stack. But having said that, if you talk to most people in programming languages, they will say that learning it through recursion is the correct way to learn it. I would recommend, regardless of anything, that you should do a course in functional programming. I don't know if you're familiar, but there's actually now in industry, there are jobs meant for people who can do functional programming, because a lot of the code that is being written in a lot of like big data companies they're only writing recursive code. They write it in Scala, which is a functional programming language, and there are reasons for doing that. So in general, I think recursion is conceptually better, but again, if you're looking for just runtime efficiency, you do it iteratively. Yeah.
Why does the return not contain a node star?
Where? Well, it's just returning whatever this returns, right? And find returns. So you can see that it always just returns a node. It returns a node star. Sorry. So maybe I didn't get that question correctly. So it is returning a node star because it's always returning a pointer to a node. Does that answer your question? Right. Yeah. Yes.
Could you go into compile time?
So compile time versus runtime. So a compile time bug is one where your code just doesn't compile, right? So you try to compile it and it just doesn't compile, which is the better kind of bug to have, rather than it finishes, it runs, and then you need to figure out where the bug is, right? So often with functional code, your code, if it's incorrect, just won't compile. So I've actually noticed this with Scala. I wrote Scala code for a summer, and it was actually quite surprising. Like when the code compiles, it's correct, which often rarely happens with C. Right? Like digging through bugs through like looking at the logs of what you did is really hard. So that's why. Okay, good. So far, so good. So that was find. So let's do delete, which is like the next natural function. Let's do delete recursively, and this is more painful. So delete is by itself kind of painful. Okay, so how are we going to do delete? So again, we'll sort of do it through find, where the return type is not void, but is node star. You can imagine the problem with having void type is if it returns, you don't know what actually happened. Right? It may have deleted, it may not have deleted. So when you return a node, then at least you have access to the node, and also it's you can if the return is null, then you know that nothing has been deleted. So okay, so it returns a node containing val after removing this node from the list. And if val does not exist, return null. Okay, so before we launch into trying to write recursive code, let's just think about the logic. So a recursive perspective is, it's sort of the obvious thing. If head arrow data is val, we'll remove the head. Right? And update, remove and update. I should say remove and update. Otherwise, you recursively, say else, recursively delete. Starting from head arrow next. Okay? Okay, so we're about an hour through the lecture. Usually I give a break now. Are people still awake? Can you continue? And I give the break 15 minutes later? Yes? No? Yeah, okay. I see some people nodding, so I'm just going to assume whoever nods vigorously has won the debate. It's almost like a sign of how politics works, right? Which is people are more vigorous and loud usually get their way. Anyway. Okay, so this logic seems reasonably sound. So let's go ahead and try to write this. I will probably do it and I'll make, yeah, go ahead. You have to check it's an empty list, right? So the 0th step has to be there, right? So this logic is by no means complete. So I'm going to actually start writing code. I might make mistakes, and then we'll see how far I get. So let's try to sort of follow the same template, and let's see how far I get. Okay, so what we'll do is let's just do like a node star delete val. So let me sort of update the head at this call and then do a recursive call. This isn't the best way of doing it, but I'm just saying let's see how this goes. So I'll say if head arrow data is equal to val. Okay? So suppose this has a val, then what do I do? Forget me making mistakes. You write the code and you make mistakes. Yeah, go on. Let me draw some pictures. Okay, so here is our favorite number 42, which we want to delete. And so head is pointing there. Yeah, so what? You can check to see if head next is equal to null. You would set the next one to head. So you check if this is null. And if it's not null, then you would set which to head? You want to do this.
Wouldn't that point head to the next?
Yes, this would point head to the next node.
Yeah, and then you would return head.
But then you would be returning this node. And you haven't removed this from the list yet. If you simply reset head to be there, this thing is still pointing to the list. Does that make sense?
Don't you delete it once you get back from the function? Isn't that the whole point of code returning and then lost it?
But you've lost head.
Yeah, I
You return the node, but you still have to remove the node from the list. There's a distinction between that, right? Yeah. Okay, you have a temp variable. Okay. Okay, so I have temp.
So then we would set temp equal to the current head, and then we can do what he was.
Then okay, so good. So now you've stored that. Then you reset the head. Okay, good. So that then so you've achieved this, and now your temp is pointing to that. So you can return temp. Yeah. Sorry, say that again? Yes, right? So you would do temp arrow next equals null, and then you can return temp. Right? So these 4 lines of code will delete that node from the list if it is the head. Yeah. It is somewhere in space, exactly. So you don't free the memory. If you really wanted to free it, then you usually will free it outside, or you could decide to free it in here. Often you don't free it here because in many, you'll see that when you do data structures, you're removing something from the list so that you can process it in some other way. And so this is to, then you would imagine that separate processing thing would eventually deal with it and free it. Which is again why people don't like coding in C and C++, because you have to do all the memory management. If it was Java, it would automatically do the garbage collection, right? So again, the reason why I do this in C and C++, I have done it in Java in the past, is so that you understand pointers. Right? This is not to say that therefore you should code in C or C++ necessarily. Yes? Exactly. So what that would do is then that would make that null. So then the list is only this. Now suppose you did not have this line of code. It would actually work. You might not find any bugs. But the problem is the node that you supposedly removed is still pointing to your list. So if you wrote code this way, then sometimes it might throw a bug and sometimes it won't, which is the worst thing ever, right? The thing about code is when it's wrong, you want it to be wrong all the time. The worst thing is when it's wrong half the time and right half the time. And then that's when, your life becomes hell. Yeah.
Do we have to add a check if there's just one node?
Good. See, I told you my code would be wrong. There. Good. Yeah.
What if the next one is...
Null?
Yeah, is it possible if we remove the head, I guess the next one, if it is actually a value, it would have to have data, so you would just be left with a linked list of 1?
Oh, yeah, so this is fine. So what happens is if head arrow next was null, which means that the original list just had one thing, then head would become null, which is exactly what you want.
Okay, so there's no two-step.
No, there are no. Yeah, no, there are no gotchas here, right? There are no gotchas here. So this is fine. But so we've only removed the first thing in the list. Now we have to do the recursion. Okay, so I'm just going to follow the template that I followed earlier. It's wrong. I'm telling you it's going to be wrong. But I'm just going to follow it, and we'll see where we go wrong. Often you learn more things by doing it the wrong way than the right way, or at least when the instructor does it the wrong way. Okay, so it would seem like a natural thing to do would be to, I'm just going to write something and we'll see how this goes. We'll return, again, I should emphasize that whatever code I've written, the correct version is there in that box, so you have access to it. So let's delete val, going at head arrow next. Would seem like the natural thing to do. Right? So you tried at the head, you couldn't, so you start at the next node. And then we write our recursive function that's going to keep going through the list. Okay, so what is, how do we do this? We can do delete node star. We have our int val. And then we have some node star start. So we'll do the base case. So we'll say if start is equal to null, return null. Fair enough. Now what? Yes? Any suggestions? So you're trying to delete starting from start, yeah?
Well, I have a question.
Yes.
What's preventing us from just using our find function? We coded earlier to find the node we want to delete.
Okay.
And just calling delete.
Good question. And you'll see the answer soon. Because what's happening here seems to be a lot like find. And we'll see that there is a problem there. So let's go through this, and then I'll ask you whether you still have your question. Okay? All right. Yeah. What next? Yeah.
Are we checking if the node after start has the data?
Checking the node after start has the data, or do we check if the node at, okay, so we could do that. But what if the node at start has the data? Okay, so check for that. Arrow, sorry, mixing up my arrow data is equal to val, right? So we have some list somewhere here. This is start. And 42 is here. Okay, so now what? Yeah? You have your hand up?
Temporary node?
Okay, temporary node. Fine. What's temp?
It's going to be equal to start.
Okay. Yeah.
Isn't the head going to be broken?
The head going to be broken.
Like, there's no way to link the head, the start of the list, to the next one?
Why?
Because we didn't pass it through.
We didn't pass what through?
The head.
The head. Okay, so I'll give you head. You have access to head all the time, right? Because this is inside the linked list class. Okay. Yeah. I didn't previous. Yeah. You have to go from the previous node, right? Right, so you need the previous pointer, which means that this recursive implementation is going to fail. The reason you often do things through recursion is so that you don't have global variables and you know exactly what's going on. So what's going to happen here is you actually need the node to the previous pointer. Yeah? You still have something to say. If you did that, then you would miss the data at start. Yes?
When we do the recursive call within the dummy function, instead of passing in head next, we should just be passing in head.
You could just pass in head, exactly, and that would take care of that. Anybody else? Right? So what you need is, you really need the node to the previous pointer. The node to the previous pointer. Okay. You need a pointer to the previous node than the one that you're going to delete, right? So let's redo this. It might be that everything that I put together might not have the right, might not be entirely correct, but we can fix it. So I'm just going to call it previous, not call it start, so that we're actually thinking that this is the previous, right? Name your variables properly. So now if this is the previous, then it's going to get a little complicated. So I'll say if previous is equal to null, or previous arrow next is equal to null. Yes, but there's nothing wrong in being safe. Often you'll be like, there's no way that could have happened, and that's exactly what will happen in your code, right? So just to be safe, Indeed, what you can instead do is you can say if previous equal to null, you can print some error message that something has gone wrong with my code, right? Just to help you debug what's going on, right? You're right that you shouldn't expect previous to be null, but you never know programmers. So then you return null. Now what you do is you say if previous arrow next arrow data is equal to val, right? So now let's go back to this picture that we had here. So this is the number we want to delete, and here is previous. Now we can write usually 3 or 4 lines of code to have this pointer skip over that, and then that node gets deleted. Yes? No? Okay, so this is a good time to take a break. So let's take a break for 3 or 4 minutes. You can step out, step in, whatever you want, and then we'll continue.
Earlier you said that the test would only be in C. Can we use C++ syntax?
Sure. Okay. Although it's, sorry. All right, let's go ahead and start. So many people have been asking me about whether the tests are in C or C++, and somehow I keep saying it doesn't matter, because if you know C++, then you would know C. But just to be clear, for the tests, the functions that you're going to write are going to be of this form. Like I'm going to say implement delete, for example, right? And so for implementing delete, even though the surrounding code may be written in C++, there's really no separate C++ syntax you need. You have to just manipulate these pointers, right? And so for that reason, I don't think if you know C or C++, you should be fine, language-wise. Yes?
For like the templating and the various syntax, do we, you said in the first hello world one, we can copy the code.
You-
Should we look at it and retype, or can we directly?
You can copy. I would prefer if you retype it, simply because otherwise our flags get, our plagiarism flags go up. So it's annoying, I know, but sorry. I couldn't see any other way around it. Yeah. And I don't do anything fancy with C++ templates and things like that anyway. Okay, so where were we? So we have access to this previous pointer, and so now we have the previous, so what we need to do is to get this pointer to skip over that and make this null, right? So, and then we would return this node here. So I'm just going to write this out maybe in more lines than I need to so that it's clear for me. So I'm just going to create a node star that I'll call the node to return. And I'm going to make this equal to previous arrow next, right? So that then means that this is to return. Then I will set to return arrow next equal to null. So I would have deleted that. Good. I need it. Good. Somebody's awake. Right? So I need it. So this would be wrong. So what's the next line? Yes.
Previous arrow next equals previous arrow next.
Yes, previous arrow next, which I can also say is to return arrow next, right? So then I would get that because previous to return arrow next is this, and previous arrow next goes there instead. Now I can remove, so now I can do to return arrow next is equal to null. And then I can return the node to be returned. Right, and then over here, this is effectively an else. Then I can return delete a val of previous arrow next. Yes? And I have to, is this logic clear? I have to go back and change something in the original function, but I'll go and do that later on. Okay, is that clear? Any questions? No, people are tired. You need caffeine or something? Yeah. So, and what you need to do here is to actually call it from head, right? Because you're sort of calling it from the previous pointer. Now, this might not be the best way to often, so deletion of the head is a separate case because the head has to change. Although the logic that you see here seems analogous to the logic that you have here. Like if you read it line by line, it's almost the same. Like the return, setting null, like. right? This logic is the same in some sense, right? But so this is, in general, if your code is failing, your linked list code is failing, it's often because the head is a special case. Either the head is empty or the linked list has size 1. Like these are the places where it often fails. List is empty, list has size 1, or you forgot to do something with the head, right? So remember these 3 things, because this is often where your code will throw errors. Or when I write code, like when I've solved some of the assignments myself, this is often where I would have made a mistake. Okay? So for the delete, the recursive delete, go back and look at it. What I would recommend is, you've seen this now, go and try to write it yourself. So you have my linked list box with all the codes there. Copy the code, keep it somewhere, and try to rewrite it yourself. Yeah? If this is null. This would not happen because you checked if previous arrow next is null.
Or if the one that you're replacing.
If that is null, that's okay, because then that would just end the list.
Okay.
Right? So if indeed, suppose to return arrow next was null. If this was null, then previous arrow next will be null, which is fine. So when you go down here, you'll do delete, and then you're calling something with null, which you'll go back and you'll fix. Yes? Sorry, where? No, that is not an integer pointer, right? That is an int. That's an int. It's not a pointer to an int. It's an int. No? No, but that's because you do a dot when you have access to the object. This is an access to a pointer to the object. Right? Because, does that answer your question, right? Previous arrow next is a pointer. It's not the object itself. The pointer to the data. Yeah, that's why you don't have the dot, yeah. Because you're dealing with the reference directly. You don't have to, yeah. Okay. Okay, good. So this was the easy part. Now let's do a challenging question now. Okay, good. So, it's a classic interview question, reversing a linked list, which if you do not do recursively is pretty difficult. Okay, so what is reversing a linked list? Here's a linked list, 42, 101, 5, 2, 3. And this is head. And so what you need to do is to reverse, it should be 3 pointing to, I don't know, whatever the penultimate thing is. 5, so on and so forth, to 25, 101, 42. And head should point here. So there are cleverer ways of doing it. There are, not so clever ways of doing it. But it's, again, we'll start with the not so clever way of doing it. Try to do it carefully. So this is an example of one of the questions I'll ask in the test. So what I've done is I've shared with all of you a box which says, I think it's called like test, or it's called reverse, or something like that. That's an example of what the test looks like. Read through it. What you need to do is to code reverse, so you can see how it's set up. Try to code reverse. I think you have to do more than reverse. You have to reverse like the first so many elements of the list, which is more challenging. Try to do it, spend time doing it. It's not that easy, right? But once you do it, I think it should be clear. And that's an example of the kinds of questions I will give. And so I've also put up a PDF with 3 or 4 different functions you should work on. Reversing a linked list, I think one is deduplicating a list. I read through those. Again, you can ask me more questions on Thursday about them. Is it about the test?
Yeah, is it the linked list, like the link on the website where you put the...
Yeah, I post a PDF there with all the questions, yeah. So try those. It will take you a week to do it. So try all of them, right? That's what you need to do over the next week. First, you write the recursive delete that I said. Try to code it yourself. Then you will code this up. And then you will do all of those. And if you do all of those, you'll be fine in the test. Because I'm just going to ask you exactly one of those questions again. Right? Okay? All right. So reversing a linked list. So the problem is the way you think recursively about this is, again, so let's do it. Okay, so I'll just say this. You can do it iteratively. You might say, well, what I can do is I can go all the way to the end of the list, delete that, stick it at the beginning, and then go down to the end, delete that, and try to stick it in the beginning or something, right? But if you do that, you'll see that you'll be dealing with lots of different pointers. It is possible. It's actually cleaner and easier to think of it in this recursive way, which is, what does it mean to reverse a list? It means the first element goes to the end, and everything else gets reversed, right? And if you try to take that logic and convert that into code, you will get the solution. So I'll write this as reverse everything recursively starting from head arrow next, right? So you try to reverse all of this. And if you reverse all of that, you should get this list. And then you insert the old head at the end of the above list. By the above list is what you got from here. Okay, does that make sense? Yes. Question? No. Yeah. Sorting a list is a different. Yeah, you can recursively sort. Yeah, that does work. So you could basically recursively sort, then go ahead and insert this in the right position. Yes. That's a good solution. Yes, you can. Now, often when they ask this question, they will say that you're not allowed to build a new list. Right? You don't want to allocate more memory than what is there. So in your solution, you'd be allocating memory. But that's a good way of thinking about it, right? So because if you insert this, then you would get a new list. So the idea would be to change the existing list. Yeah?
Would you call it with the previous and the next node, and then just call until you get to the end of the list, then start having the next node point to the previous?
You mean, you have to be a little, well, okay, so I guess you could do that. Like, you mean go all the way to the end and try to get the pointers to point backwards. But then you have to store all these pointers somewhere. And suppose I don't let you, and I'm not giving you an array where you can store them. Kind of, if you put it in an array, then that's sort of defeating the purpose of this.
What is there in the argument of the function call?
But how many are you? You can't pass all the pointers in the argument. So let me write what I'm going to say, and it will probably be similar to what you're suggesting. Yes. You could, yes, when it's like saying that you go through this one by one and you keep trying to flip these pointers. You have to be really careful that you don't lose whatever is there in the list.
You have to like point it back after you've already passed.
Yeah, so you have to pass it and then point it back. You have to be careful, which is why this is considered sort of a challenging question. And then you have to be careful with the head. You have to make sure the head then points to the end.
Yeah, when the next is rolled, then you make that.
And then you make that head, yeah. Yeah?
For like changing for allocating new memory or changing it, will you specify in the problem whether we're allowed?
Yeah, usually, so in all of the questions, the linked list questions, you're not supposed to allocate new memory. You're not supposed to build a new list. Right? You have to do it with the existing list. And this is, again, I mean, the reason to do this is not because, people go around coding up, reversing linked lists in data science companies, but so that you get, your logic about arguing about pointers improves. Right? That's sort of the aim, yeah?
Actually, never mind. I'm still thinking about it.
Okay. So what I'm going to do is I'm just going to write out not full code, but sort of the basic idea. Right? I'll give you a structure of the code, and you should be able to convert this. On Thursday, we can talk about it again if people want. So thinking recursively, okay, so you'll have to figure out how to call, like, what is the dummy function? Like, what is it that you have to call? It should be reasonably obvious. But let's start with just this function that from some intermediate node. So this, I'll put the star there, returns I'll say the beginning, and we'll of reversed portion after start. Okay, what this means is, okay, I'll draw a picture here. Let's say that this is start. So what this function is going to do, it's going to reverse that. So if this node is 5 and that is 2, it will reverse that and then give you this pointer. That's what I want this function to do. Yeah?
So wouldn't that be including start rather than like after?
Yeah, so after is including, you know what I mean. Start plus after start. I didn't. It's unfortunate that there's no word for that, right? That this and everything else. So yes, all right. So how would I do this? So I would have some if start is null or start arrow next is null. Right, so if it's null or if it's just one node, there's really nothing to reverse. So I'll just return start. And that's the base case. Start is our current, yeah. But I call it start because it's like the starting of the portion that you're looking at. It's a start of the portion that you're looking at. Okay, so I'm not saying this logic is entirely correct, but this should give you the basic idea. So what is, okay, so let me write this. New start is equal to reverse start arrow, which means that I look at this part and I reverse all of it. I get everything here. And recursively, I already have the beginning of of the new reversed portion, right? Because the only difference between the reversed portion of this and the reversed portion of the 5 and everything The starting of the new start of the reverse portion is the same. It's just that this node has to go at the end. Does that make sense? Okay, so now what I'll say is node star tail, which is I'll say get the end of the above portion. So I want to get, this is tail. This I can do just by sort of traversing the list. Once I get the tail, now I'm just going to sort of write in English. Insert node at start, which is that node, at the tail. Right? So you need to insert this node over there, making sure that that becomes a null. And then you would return the new start, which is this. So you have to be, okay, so we're basically out of time. So I'll just say that I can complete the discussion of reversing next time. I want you to try it out using this logic. The logic being you have a recursive function that starts at a node